Okay guys, we're starting on our last day of 10.1. This is 10.1 day 3. After this, you should expect to see some kind of an assignment that is not from our sapling program. And we're just going to get started here. Let's take out the handout. According to phys.org, Black and Hispanic females are underrepresented in STEM programs compared to non-STEM programs. A certain university would like to see if this is true for their student population. So right here we're going to pause it and say that we are comparing the population of a certain university with the theory espoused by phys.org. So there's our comparison already. They took a random sample of 300 STEM students and found that 12 were Black or Hispanic. So that sounds like 12 out of 300 for one of our proportions. A separate random sample of 500 non-STEM students had 75 Black or Hispanic students. So that sounds like 75 out of 500. So let's go with next, which is do the data provide convincing evidence that Black or Hispanic females are underrepresented in STEM programs? We're using a 5% significance level. You can go through this over here and you're going to see that this is all just state, plan, do, and conclude. The same 4 things that we've been working on for so long now. Hopefully it's down to a science at this point. So parameter, what is our parameter? Well, we're saying PF minus, PS, STEM. PS minus PNS is equal to the true difference in proportion of proportion of Black and Hispanic females in STEM and non-STEM. So that's kind of a mouthful. But it is a true difference in proportions of Black and female students in STEM and non-STEM. What is our statistic? Well, that's P S hat minus P NS hat. So what does that equal to? Well, the STEM was highlighted there. We had 12 out of 300 in STEM. Okay, so 12 out of 300. Minus, and then how about for non-STEM? That is, out of 75, or out of 500, we got 75. So that's 75 out of 500. And let's just ask Alexa what that is. Computer, how much is 12 divided by 300 minus 75 divided by 500?
12 divided by 300 minus 75 divided by 500 is minus 0.11.
0.11 negative. Okay. Hypotheses. Well, first one is P STEM minus P non-STEM. Well, if we're testing to see if there is a difference, then our alternative hypothesis would be that there is no difference, which means that PS minus PNS would be equal to 0. However, if there is a difference, we want to test to see if STEM is lower than non-STEM. So if STEM is lower than non-STEM, then the arrow has to point this way. You can imagine doing some algebra here, adding the proportion of non-STEM to the right, and you would get the proportion of STEM is less than the proportion of non-STEM. Significance level, that's 5%. Okay, so that takes us through all of our state part. Let's do the name of this procedure. This name is a 2-sample z-test for P1 minus P2. Okay. Basically just like yesterday, except for instead of an interval, we're doing a test. Okay, let's check our conditions. Random. I'm going to scroll up and see if there's anything here that says random. Let's highlight that in blue. Let's see. Random sample and the separate random sample. Okay, so we've highlighted that. That doesn't really count for a whole lot. We need to write it now. So we have random samples. Okay, so that's going to have to suffice for our randomness. The next part here is 10% rule. So 10% rule, our first sample was 300. So 10 times ns is equal, I really shouldn't use that n. I should use a lowercase n. 10 times ns is equal to 3,000. And then 10 times the number of non-stems, that's equal to 10 times 500, or 5,000. So do we know that this university has more than 3,000 STEM students? Do we know if this university has more than 5,000 non-STEM students? Well, I think we're going to have to assume that because we don't know how big this university is. 8,000 people, and that's not a small university. Certainly not a big one. I mean, we live at the doorstep of UCLA and Cal State Northridge. Those are big universities. These guys are not nearly as big, but we'll have to assume more than 3,000 STEM and 5,000 non-STEM students. Because again, we just don't know how many students there are. So this is the appropriate time for us to write assume if we don't know. Okay, assume means we don't know, and we're going to pretend that it's true. Next, what about large counts? Okay, I know I'm using large counts and not fluffy, as we call it in my stats class. In our stats class, we call that fluffy, because we're using proportions here, and proportions are always about large counts. So the first one is N1 PS hat. And what is that equal to? That's equal to 12. Okay, and certainly that's greater than or equal to 10. How about N1 QS hat? That really should be NS also. NS QS hat. Well, that's going to be the rest of them, which I believe is 288. Yeah, 288. That's also greater than or equal to 10. Let's take a look at the non-STEM students. The number of non-STEM students multiplied by the proportion that of non-STEM students that are black or female, that's equal to 75. Remember, it may seem like I'm doing multiplication really fast, but I'm really just looking at the number of successes. The next one is NS QNS hat, and that's equal to the remainder there, so 500 minus 75, that's 425. Both of these quantities are greater than or equal to 10. So what we're saying that now is that if we combine those two, or if we take them separately, both of them are going to give us normal distributions. So we're good to go on the plan part. We have normal distribution, and now we just go ahead and do the do. I don't know. What is the mean of this? This is of P1 minus P2. That is equal to 0. How do I know that that's equal to 0? Well, because that's from our null hypothesis. null hypothesis, which I forgot to write null hypothesis here and alternative hypothesis here. So our null hypothesis tells us that PS minus PNS is equal to 0. Therefore, the mu of P1 hat minus P2 hat is also equal to 0. What is a general formula for any hypothesis test? Well, that is the test stat is equal to the statistic minus the parameter over the standard deviation. Specifically, we're dealing with proportions, so this is a z, and our statistic was, what was that? Negative 0.11. Negative 0.11. Parameter, remember that comes from the null hypothesis. When we're doing a difference of proportions, we're always pretty much going to be 0 there, unless you're on question 6 on the FRQs, in which case maybe it won't be 0, maybe it won't even be this kind of a question. Who knows? But as we know, question 6, all bets are off. So this is 0. Our standard deviation here is going to be, well, what is our standard deviation here? Okay, so this is where things really change for us. Because if you take a look at our null hypothesis, and this is actually the major difference between this and the interval. In our null hypothesis, we're saying that these two proportions are the same. And if these two proportions are the same, that means that we don't really have two proportions. We have one proportion, and both of these are estimates of that same proportion. So really our sampling distribution should be based on that one proportion that that comes out of assuming that P1 is equal to P2. So that proportion, that one proportion, we're going to call PC. Okay, so this is going to be PC hat QC hat over N1 plus PC hat QC hat over N2. We'll get a much nicer look at that later on. So let's do our work. First of all, let's figure out PC hat. Okay, that's going to be the total number of successes in the first sample plus the total number of successes in the second sample, all divided by the number in the first sample and plus the sample size in the second sample. So for us, that means our 12 and 75 divided by our, 300 and 500? That gives us a PC of, let's see, that's 87 divided by 800, I think, 87. Computer, what's 87 divided by 800?
87 divided by 800 is 0.1088.
0.1088, so let's make that 0.09. That's our PC. So now when we do our Z, that's going to be equal.
I'm not quite sure how to help you with that.
Of course you don't. 0.11 divided by square root of, 0.109 times 0.891 divided by 300 plus 0.109 times 0.891 over 500. Remember, this is a consequence. Using PC is a consequence of assuming that P1 is equal to P2. That's why we do it. That's why you don't use the same standard error that we used for our confidence interval. Okay, I think we're ready to go now. You know what I should do? I should fix this right here. I realized this was supposed to be the specific formula and not the work. Maybe you were tearing your hair out here when I was doing this. But our specific formula is P1 minus P2 minus 0. Those should be hats, and rather than a 0 here, we should say it's P1 minus P2. Okay, which is basically 0. That's going to be 0. Almost always. In fact, I don't think I've ever remember a time in AP Stats where that's not equal to 0. But that's far different than saying that it's always going to be 0. Okay, so let's calculate this, and what do we get? We get, well, no, we should put this in the calculator. What am I doing? Let's put this in the calculator. You have negative 0.11. I don't know why a comma came out. Negative 0.11 divided by square root. I don't like that. Let's get our fraction bar. Negative 0.11 divided by a square root of, I think we need another fraction bar here. Okay, 0.109 times 0.891 divided by 500. No, that's 300, my bad. Plus, get another fraction bar. Okay, 0.109 times 0.891 divided by 500. Okay, a moment of truth. Hey, negative 4.83. Is that a 3? Yeah, negative 4.833. So our z is equal to negative 4.833. Okay. Moving on to the picture that we have drawn. Here's our standard curve. This is where 0 is. And that has a z-score of 0 as well. Remember, 0 is the center of our, what do we call it? The center of our sampling distribution that we get from our, pointing the wrong way, from our null hypothesis. Okay, and negative 0.11 is way off over here. Negative 0.11 with a z-score of negative 4.833. Our alternative hypothesis was less than, so we're only looking at this area here for the p-value. So let's calculate that p-value right now. I'm going to take out the calculator yet again, and we're going to say distribution. This is going to be a normal CDF. Our lower is negative 1e99. Our upper is negative 4.833. 0 and 1, because these are all z-scores. And, we should be getting something really close to 0 here. Yeah, that is 0. That is 6 zeros followed by a 6. Okay, so our test statistic z equals negative 4.833. Our p-value is a probability that z is less than negative 4.833, which is equal to I think we said 6 zeros, 1, 2, 3, 4, 5, 6, followed by a 6, which is basically equal to 0. Conclusion. If the p-value is low, that means that we have evidence for our alternative hypothesis. So since the p-value, which is 0, is less than alpha, which is 0.05, we have evidence, or the data shows that the true difference, if the true difference, we're saying that the true difference is less than 0, and if we're saying P1, Pn minus Pns is less than 0, what we're really saying is Pn is less than Pns. So the true proportion of Black and Hispanic females in STEM is less than that in non-STEM programs. Okay, so really this proceeds along a lot like any of the other hypothesis tests that we do. The main difference is that we're figuring out that PC for our standard error. So let's take a minute here and go to the stuff in our important ideas. They're really small today. Let's get that a little bigger for you to look at. Okay, so the major changes to the 4-part plan, everything else is just the 4-part plan. So our hypotheses are different. Our hypotheses have P1 minus P2. Our alternative hypothesis, it's still P1 minus P2, greater than, less than, not equal to. You pick the one that best fits the problem. And then the huge change for us is this PC business, which affects our standard deviation. The shape is still a normal curve. We still do randomness, 10%, and large counts. And once we get our test statistic, that's basically the same formula. It's the stat minus the parameter, which is the null, divided by the standard deviation. Okay, so you can pause it here to do that. I'll give you 3 seconds to push the pause button. 1, 2, 3. Good. Let's check our understanding down at the bottom. To study the long-term effects of preschool programs in poor children, researchers designed an experiment. They recruited 123 children who have never attended preschool from low-income families in Michigan. Researchers randomly assigned 62 children to attend preschool, paid for by the study budget, and the other 61 will serve as a control and would not go to preschool. One response variable of interest was the need for social services as an adult, and over a 10-year period. Wow, that's a really long study, a 10-year study. Could you imagine that? Over a 10-year period, 38 children in the preschool group and 49 in the control group have needed social services. So do these data provide convincing evidence that preschool reduces the later need for social services in children's like the one in this study? Justify your answer. So that justify your answer right there, that's code word right now for 4-part plan. So let's do it. State. Okay, so we're saying P1 minus P2 is equal to the true difference in proportion of children that need social services later in life. True difference in proportion of children, preschool and non-preschool, I should say. Preschool and non-preschool. Okay, and let's get our significance level. Our alpha, they don't tell us an alpha, so we're going to use 0.05, whichever alpha you like, as long as it's one of the ones that we always study. So let's do P1 hat minus P2 hat. That's going to be necessary for us. That's going to be, what is this? 38 in the preschool out of the 62 that were given preschool, minus the 49 over 61. Those are the ones that were not in preschool. Computer, how much is 38 divided by 62 minus 49 divided by 61?
38 divided by 62 minus 49 divided by 61 is minus 0.1904.
1904. So let's just use the first two digits there.
The answer to your calculation is 40,194.
Thank you. Alpha equals 0.05. Oh, we already wrote that. What am I doing? Okay, I think that's the end of our state. I'm gonna even put this in a box, just like I don't know. Plan. This is a 2-sample z-test for P1 minus P2. Just as a comment over here, since we're defining P1 minus P2 as being a difference, I imagine that we're okay not defining what P1 and P2 actually are, as long as we know that P1 minus P2 is that difference. Which one of those two plans are better, defining P1 and defining P2 separately? I don't know. As long as you're consistent and you know what you're doing, I imagine it wouldn't make too much of a difference. But let's just continue. How about our conditions? Okay, so condition 1. Are these random samples? Is there anything in this that says random? Let's see. They randomly assigned. Okay, so random assignment, yes, that counts. So random assignment. So we have random assignment. Okay, that's our first one. Our second one is 10%. So let's see, 10 times n1, that's equal to 610. And then 10 times n2, that's equal to 620. So this is probably true. So there should be, or reasonable, that there are more than 610 and 620 preschool / non-preschool. Yeah, you'll have to excuse my handwriting. It's getting really bad. So I'm going to slow it down a little bit, try to write a little bit better. The last one is large counts. So N1, P1, that's equal to the number of successes. That's for the first group, the preschool group, that is 38. Certainly greater than or equal to 10. So that means N1Q1, that's got to be equal to, why did I write 30? That's supposed to be 38. So 38 from 62, that is 24. So 24 is definitely greater than 10. How about N2, P2? And these should be hats, really. That's equal to 49. Certainly that's greater than or equal to 10. And that would mean N2, Q2 hat, that's equal to 12. Also greater than or equal to 10. Okay, we have satisfied everything, so we have a normal distribution. We don't actually have the numbers to put in here yet. Oh yeah, we do. We know this one. This is going to be equal to 0 from our hypotheses. Oh, major failing, Ferraria fail. Our null hypothesis, P1 minus P2 equals 0. H alternative, P1 minus P2 is, let's see, we think that social services will be required, there'll be less proportion from the preschool group. So this is the reason why, right over here, this is the reason why we get that 0 there. Okay. We're going to have to compute the, how do you say this? We'll compute the standard deviation pretty much right now. So the next part is do. Let's do some stuff. The test statistic, that's equal to the statistic minus the parameter over the standard deviation. Specifically, our z-score is equal to P1 minus P2 hats minus P1 minus P2 non-hats divided by the square root of PC QC over N1 plus PC QC over N2. While we're at that, let's figure out PC. So PC is going to be equal to the total number of successes, which would be 38 plus 49, over the total sample size, which is 62 plus 61. Let me add those together. 30 and 40 is 70. 70 plus 17 is 87. On 60 plus 60 is 120. So 123. Computer, how much is 87 divided by 123?
87 divided by 123 is 0.7073.
0.073. Repeat that.
Sorry, there is nothing to repeat.
Computer, how much is 87 divided by 123?
87 divided by 123 is 0.7073.
7073. How much of that should we use? I think maybe just using 2 decimal places here should be enough. Oh, what did I just do? That's gross. So maybe 0.71 is going to be enough for us. Okay, now for the specific substituting our numbers in. This is going to be, and we already calculated this, this is negative 0.19 divided by the square root of 0.71 times 0.29 divided by 61 plus 0.71 times 0.29 divided by 62. Okay, let's put all of that in our calculator. There's our calculator. Let's get our fraction bar. So negative 0.19 divided by, and radical, fraction bar, 0.71 times 0.29 divided by 61 plus fraction bar, 0.71 times 0.29 divided by 62. What does that get us? That gets us negative 2.322, negative 2322. All right, how about a drawing of our curve? I think that's what comes next. Okay. Over here, of course, mean is 0. That's a 0 over here. Over here is negative 0.19 and has a z-score of negative 2.322. Here's our p-value. Our alternative hypothesis was less than. So we're going to shade to the left here. That looks like a very small p-value, probably less than 5%. We're coming to it now. We're going to use our normal CDF, negative infinity to negative 2.322, zeros and ones because we have z-scores. Pasta, 0.101. So the p-value is equal to the probability that z is less than negative 2.322, and that turned out to be 0.01. I forgot the last two decimals. 0.01. How do I forget 0101? Okay, that is definitely a small z-score. So now we can conclude. Okay, so since our p-value, which was 0.0101, is less than alpha, which is 0.05, we have evidence that the true proportion of preschool students that need social services let's get some more room here. Services later in life is less than that for non-preschool students. Okay. Based on your conclusion, could we have made a type 1 or type 2 error? Remember that a type 1 error is the error that you would make if you reject the null hypothesis. Type 2 error is the error that you would make if you fail to reject the null hypothesis. We rejected the null hypothesis, so we're in danger of the type 2 error. I'm sorry, type 1 error. Since the type 1 error is an error of false rejection. Okay. So what that would mean is that we think that the proportion of preschool students who need social services is less than that of the non-preschool students, but that's wrong. Either they're equal or non-preschool students actually have a lower social service than preschool students. So basically, we made an error in that case. So that's it. How long is this one? These all seem to be running really long now, but we are at, oh my gosh, that was a really long one. And yeah, I don't have anything else to say to that. So have a nice one. Do your sapling. See you next time.